I want to give you 3 quotes. The first one states that the world is sound, nada Brahma in original Sanskrit. Since both these words have a variety of abstract meanings, it can also plausibly be translated as the nature of the universe is vibration. The second one is widely attributed to Nikola Tesla, and though there isn't much evidence that he did say it, we're going to run with it anyway. It goes, if you want to find the secrets of the universe, think in terms of energy, frequency, and vibration. And lastly, quite recently in 2009, Stephen Strogatz, a mathematician at Cornell University, playfully writes that the laws of nature are written as differential equations. There's a common core to all of these statements, a very abstract idea that separates the material world from the chatter of echoes passing through its body, and the radical suggestion that such echoes, rather than any fabric, are the true nature of observed reality. In this video, we'll explore this perspective by examining waves and vibrations, the basic units of information taking form and interacting with each other, and tie it together with millennia-old insights about the nature of the universe. I hope you enjoy. Let's first understand what waves and vibrations are, mathematically speaking. A common image that comes to mind is what happens if you take an end of a rope and whip it up and down to observe a wave-like pattern traveling through it. Your hand is doing the vibration part, harmonic motion back and forth between two positions, and the rope becomes some analog of a medium through which the wave travels. Doing this with enough intensity and assuming that the rope is long enough, it looks just like a sine wave that magically comes out of your hand and travels linearly away from you. In real life, the rope will pull towards you, there's gravity, and it will bounce off the ground and do chaotic things. But we're not interested in any of that at this point. We want to look at pure, idealized waves. To begin making a model for them, we're even going to ignore that they have to initially come from somewhere, and instead just imagine an eternal wave that permeates all of space and travels forward, something like this. In our model, space has one dimension and it's addressed by the variable s, just a single dimension coordinate. There's another variable, t, of time that we let flow naturally instead of assigning it to an axis on the screen. We can now define a function, let's call it u, that takes s and t as parameters and gives the vertical offset of a wave at a position in time and in space. What could the function u be? A simple sine of t minus s will do the trick. There's a minus between, because if you fix a position in space and let time flow, you get the same result as if you halted time and traveled backwards in space. We could also have done it the other way around, and in all the demonstrations so far you wouldn't see any difference because this is just the same as shifting sine by half a period, pi, so it's exactly the same wave in a slightly shifted coordinate system. This is the basic form that we can shift and scale into any one-dimensional elementary wave. Let's see how this works. We're going to take our basic wave function and add scaling factors to the function itself and its arguments, like this. It then simply expands into a parameterized wave function. These factors are typically labeled as a, omega, and k, and affect the height, speed, and compression of the wave. Of these, I think a for amplitude is the most straightforward. But the other two, their names are angular frequency and wave number, which, if you're seeing this for the first time, probably won't mean much to you. I think the best way to understand it is to look at the dimensions in which a wave exists. We've got one-dimensional space, s, which maps to the medium the wave propagates through. The value of the function, u, doesn't necessarily have to be another dimension of that same space, like it is for visible ripples in a material. It could be an electric signal, for example. It's truly independent. We'll call it signal space. Next comes time, nothing extraordinary there. And there's another less obvious one we'll label phi, that controls how far along the repeating pattern of the sine wave we are. We call it phase space. It has the value of everything inside the sine function, And since it's just angles, it also has the property that any two values 2 pi apart are equivalent. Since this expression for phase is a linear equation, we can also use it to connect the changes in phase, time, and space, and then use that to find more intuitive wave parameters. Let's start with frequency. We want to find the movement of f full cycles in phase during 1 unit of time happening in the same point in space. That lets us express omega in terms of the regular frequency. There's nothing fancy going on here. I'm just expressing frequency in terms of change in wave parameters and loading that into the expression above. For wavelength, we want to find the distance in space lambda, that's just a letter we're assigning to wavelength, that covers one complete period, measured backwards, so we end up with a positive value, while time stands still. From that, we get k in terms of wavelength. And finally, we also want to be able to express the speed at which the wave is moving, c. For that, we're looking at points that move in both time and space without change in phase. So we want the ratio of change in space and in time to be equal to our speed, and the change in phase to be 0, which allows us to express speed as a ratio between our original parameters omega and k, and also discover that frequency and wavelength multiplied together give us the wave speed. This is the basic framework for expressing waves, and from here we can build something more general and closer to nature. We'll start by focusing on what happens to a wave in one fixed position in space as time flows. To keep it simple, we'll just set s to 0 and set that equal to a function h of only time. That's just the wave function with the dropped space component. It gives us this regular back and forth movement we call harmonic motion. The harmonic thing about it is that it emulates a balanced periodic system that, once we get it going, in principle keeps oscillating forever, like a weight on a spring. We'll quickly notice that our oscillating object continuously changes speed. It has no choice but to do this because it's the only way that it can keep moving but never get away. This change in speed is described by acceleration induced by the net force acting on the weight. A force that always pushes the weight back towards the equilibrium, the center, and grows with the distance from equilibrium. Since acceleration is the second derivative of position, we can see that behavior in the second derivative of the h function. It works out to minus omega squared times a sine of omega t, an expression that contains the original function h here. So we can express the second derivative, acceleration, as a constant term, minus omega squared, times the original function. What this is saying is that acceleration is directly proportional and in the opposite direction of the distance from equilibrium. And because of this relationship, this kind of system, called simple harmonic motion, ends up self-balancing. This kind of equation, where a function is related to one of its derivatives, is called a differential equation. It's quite powerful. In our specific example, this expression alone enforces and extracts the essence of simple harmonic motion, even without specifying what the function h is. It turns out that it must be a sinusoidal form to satisfy it, but writing it in this way lets us pin down this behavior and separate it from a specific function that implements it. Let's now bring that back into the context of waves. To express the propagation of a wave, we need to capture both the movement that induces the wave and the way that movement travels as a signal across space. In this animation, we have a clear source at the start, and we already know how the second derivative relates to position at this point. We can rewrite that for our function u like this. We'll get the same result if we take the second derivative where the position in space is some other number, like 2. In fact, this works for any fixed position in space, but we can't clearly write that in this notation. We need the Leibniz notation for partial derivatives, something that looks like this. It may look a bit scary if you haven't dealt with it before, but remember, this is the same as what we've done with the 0 and 2 cases. We're just treating the argument s as a constant and otherwise working out the derivative the normal way. This is called a partial differential equation. a relationship between a function and its derivatives, where some arguments may be fixed. So now, why is this true everywhere in space for this function? Away from the moving arm, where is the acceleration coming from? We'll get a hint about that when we take the second derivative with respect to space, using the same trick of treating the other variable, time, as a constant. For 0, we'll get the original function multiplied with a negative k squared. This also works for any position in time. It's the same behavior, a proportionality with a constant, and here it represents a recording of harmonic motion baked into space. Now we can transform the expression on the right into what we got on the left by multiplying it with omega squared over k squared. That lets us relate the two partial differentials. And if we remember from earlier, omega over k is actually the wave speed, so we can write it more elegantly in this form, known as the wave equation. This couples the regular acceleration in time to an acceleration in space. Acceleration in space is a mathematical way of describing curvature, the local shape of the signal. Is it now bending up or down? Positive values mean it's swinging up, negative down, and 0 is a straight line. The wave equation tells us that localized motion changes shape and the changing shape drives motion, and these two effects are coupled with a square of a constant that represents the speed of the wave. Coupled differentials reflect the way change naturally propagates, which is always indirect. In nature, nothing is really rigidly attached to anything else, not if you look close enough. If you kick one end of an object, what actually happens is that you displace particles you come into nearest contact with. The other particles move because their neighbors have moved, trying to find their way back into a stable lattice position relative to them. Each of them needs to individually speed up from a standstill, which takes a bit of time. This is what kills the immediacy of the transfer of motion and what sets the wave speed, also known as the speed of sound for a material. It is typically higher when a material is denser and its molecular bonds are tighter. With the wave equation, we've again extracted a behavior out of a function. And while the equation for simple harmonic motion allowed only one simple sinusoidal form, with a freely chosen phase shift that we skipped for simplicity, the wave equation is a bit more permissive. Since the derivative of a sum is equal to the sum of derivatives, the wave equation also works for a sum of waves traveling at the same speed. It even works for the same speed in the opposite direction, so we can mix waves of different wavelengths, phase shifts, and directions, and what we get still satisfies the wave equation. We call this a superposition of waves because they overlap in both time and space, and also because their individual properties still shine through in some respect we'll talk more about in a later video. Adding up a few different waves, some of which are going in the opposite direction, it looks like the surface of water sloshing around, because it is a very good approximation of how the surface of water behaves when it's disturbed. And maybe surprisingly, there is no limit to how well we can represent an arbitrary signal by adding up sine waves. Fourier proved this in the early 19th century and even gave us methods of finding these components in a composite signal that we today call Fourier analysis, which we won't go into today. This form of the wave equation is perhaps the most pure expression of information propagating without any outside influences and in one dimension. In reality, we add a lot more terms to the right-hand side of it. First off, we spread it into more dimensions by adding more spatial curvature terms, and yes, it really is that easy. And then we add more coupled mechanisms, like energy loss or effects of other physical systems that feed, hinder, or interfere with our wave. Accounting for enough of them can give us amazingly accurate models of how the real world behaves. And then there are many more differential equations for physical systems. In fact, almost everything we have a description for in physics is, in its most general form, a set of differential equations. Being able to describe almost any physical phenomenon by finding and adding up rules around single points tells us a fascinating story about the nature of reality. We are, after all, just tracking some abstract values assigned to points in space, like pressure, temperature, electric potential, and so on. concepts that summarize and represent the arrangement and activity of matter, or at the lowest level, the state of quantum fields in an area. We are expressing how information useful to us interacts and propagates. So let's take a step back and set our imaginations free. If we leave aside exact modeling and computation and think only of the base principle of continuous interaction between adjacent bits of space, which drive their neighbors and their neighbors drive them, and realize we're free to assign the variables that oscillate to anything we want, there's a kind of world that emerges. A world that animates the world of matter, an eternal buzz of propagating change. Messaging and nutrient exchange between cells, currents in the air, temperature variation, all interconnected, all an echo of what happened just before and just nearby, but also a distant echo of events that happened earlier and further away. Even our memories, intentions, and relationships have this nature, because they are not matter itself in the same way that a video or a website aren't matter. They can be imprinted on matter, and matter can enact their form, but they themselves are not material. This video itself is an amalgamation of pixels vibrating around their color values. They were arranged to vibrate in this particular way by me, a human being that exists somewhere in flesh that you've never seen. You can imagine that the flesh must exist, but at the end of the day it's not really relevant because that's not what you're interacting with. You're interacting with the disturbances of matter that happened because of the disturbance of matter that I am. And as for my body, in roughly 7 years, most of the matter that makes it up will part ways with the cloud of identity associated with me. Don't worry, I'll be fine. It just means that my body will be recomposed from particles in my environment. The matter I'm made of is only associated with me in passing. What I'm saying is, your consciousness doesn't directly live in the material world. It lives in a soup of echoes organized into identities and meanings. Matter plays the role of a medium through which these echoes propagate. There's a way to see the reality above and below the material substrate as the actually significant real world, because what's below explains its nature, and what's above is of that same nature and most directly relevant to us. And that is a gateway into what is meant when we say the world is sound, Nada Brahma. Early Hindus didn't think in differential equations for sure, but they did without doubt recognize that vibrations build worlds. Their earliest stories present us with the idea of a sacred primordial sound, Aum, that the universe arises from, making everything within the universe that exists today its reverberation, which has interesting similarities to what we now think of as the Big Bang. We do, to the best of our current understanding, live in an echo of fluctuations in the earliest moments in our universe, blown up dramatically in time and space. Today we have direct evidence of the expanding universe and wave properties of many things beyond sound itself, and it can seem like people thousands of years ago just made some very lucky leaps of faith. But there's more to it than that, even putting mysticism aside. Some fundamental properties of nature could have been revealed to careful observers even thousands of years ago without any special equipment. Sound itself, when studied in reverence, and especially through the practice of music, hints very strongly at a deeper truth about how energy coalesces into persistent forms. And running the clock back in one's mind on such processes plays out remarkably similar to the rewinding of cosmic expansion. That's what we'll focus on in the next episode of this series, where we dive into the world of resonance, a concept of great importance in both its mechanistic and spiritual meaning, and the taste of the power of creation through the rules of harmony. Thank you so much for watching. I hope you enjoyed and learned something new. Tell me what you think about these threads connecting modern understanding with deeper questions our human nature drives us to ask. And have you thought about waves in this way before? Let me know in the comments below. Please subscribe and select the bell so you get notified as new episodes come out, and you may want to check out my other videos. I do it all with love. Until next time.